you very much, and I would like from the bottom of my heart to also thank those who invited me, because it means a lot to me, and in fact falls into a pattern why this year is particularly good for me and has been very successful. I was able to resolve two festering inferiority complexes that I had for a long time. The first one I resolved when, back in April, I went on a vacation to Israel. And it was getting very embarrassing with my Jewish friends to admit that I have never been there before. The second one I resolved just 2 days ago when I came here to Santa Barbara. It was getting very embarrassing to having to admit to my theoretician friends that I have never been here. And as you can imagine, due to my background, these are two largely overlapping groups of people. So with many of my best friends, my standing has increased substantially this year. So thank you very much for inviting me. So I will talk about a new member of an old and very well-known family of materials. My talk is largely going to follow the lines of the talk that my PhD student, soon to finish, Leonardo Faccheris, has given at the March meeting, although we do have some results that we didn't show then. And it's, most of the work was done in our group in Zurich, but of course we completely relied on the help and the goodwill of our collaborators at user facilities for neutron scattering, and also it was a very nice collaboration with Estonia, with Professor Rome and his people for terahertz studies. Yeah, so I'm not going to present some grand vision today. I'm talking about one particular material, but this material, realizes one of the most important models that we have in frustrated magnetism, and this is the distorted triangular lattice. So you have a triangular lattice of magnetic ions, antiferromagnetic coupling everywhere, and you have coupling J in one direction and coupling J prime in another direction. And the reason, as you well know, why this model is so interesting, because it is a vehicle for bringing exotic physics of one dimension into 2 dimensions. The idea is the following, that you would say, well, you could take spin chains and you could couple them with, say, a rectangular lattice. But the problem there is that, as you know, an antiferromagnetic chain has infinite susceptibility at Q equals pi. So as soon as you couple it in a non-frustrated rectangular manner to form a 2-dimensional network, you will get long-range order at this wave vector. You will get an EL state. And here you're trying to use this trick by having a completely frustrated coupling that would not amplify those antiferromagnetic correlations in the chains and would not result in at least a robust EL order. And this has been realized many years ago. And these materials was the formula A2TX4, where T is a transition metal, A is an alkali metal, and X is a halogen. These have been known to be very good realizations of this model for a long time. And here is some beautiful data that has had a very big influence on the field from Radu and from Alan back 2001, where they studied cesium copper chloride in a whole series of papers. But one of the first things they did, they realized that the excitations in the system are nothing like you would expect in a classical ordered material, but rather are a broad continuum of excitations that you could interpret in the language of excitations in the RVB spin liquid, or you could talk about the weakly and frustrated coupled chains importing the spin-on continuum into 2 dimensions. And even more interesting physics is revealed, as you know, in applied magnetic fields, and there are all sorts of phases and excitations that are sometimes reminiscent of 1D physics, sometimes are really 2-dimensional triangular lattice-ish. And here is a plot from a 10-year-old paper by Leon and Oleg, who have studied this. And you see that you have these spin density wave phases, for example. I will talk about those a bit later, that are really come from 1D physics and from incommensurate correlations that develop in spin chains in applied magnetic field. But you also have, for example, this up-up-down 1/3 magnetization plateau that, thanks to the groundbreaking work of Andrey and Denis Golosov, We know that is intrinsic property of a triangular lattice, that you have a magnetization plateau, quantum fluctuation stabilizing the up-up-down state compared to, for example, the cone phase. And in these materials, both types of physics have been observed. So like something that has to do with 1D, but also the magnetization plateau has been, one-third plateau has been seen very nicely in cesium copper bromate. And you can change the cesium part, you can change the halogen, but today I will tell you what happens when instead of a spin-half copper, which is close to being a Heisenberg case, you introduce cobalt, which is, of course, allows for strong single-line anisotropy. So as I already mentioned to Alan earlier, the only reason this material has not been studied, I think, is that unlike the copper-based systems, it doesn't grow from solution. So you have to grow it in a furnace. We use Bridgman method, but you can grow very nice crystals. And they have essentially the same structure as cesium copper chloride. You have these triangular lattice, distorted triangular lattices in the BC plane. So the unique and stronger exchange interaction is along the B axis. And then you have J prime that couples and so on and so on. So you have these planes of triangular lattices. But of course, instead of copper, you have cobalt, and cobalt is 3+. And there is the local crystallographic electric field, which splits the doublet into a low-lying plus minus spin-a-half doublet, the four states into a lower and higher energy doublet, the lower one being plus minus spin-a-half because this is an easy plane anisotropy. And one thing that is introduced here compared to the copper system is the anisotropy, which is mostly planar, it's XY, but there is a caveat that if you look at the orientation of the anisotropy planes, they are different for these spins and these spins. So these are easy planes, but they're easy planes that are almost orthogonal in neighboring chains. So if this is the triangular plane and these are my chains, then the anisotropy planes go like this. And the angle between the anisotropy plane and these spins is almost 90 degrees. So it's a weird model and a little bit artificial, but as you will see, it gives rise to very, very pretty physics. So this is a complication, but fortunately, most of what I'm going to be showing you today has to do with the lower doublet. And the splitting you can estimate from thermodynamic measurements, for example, is about 14 Kelvin, so 1.5 millivolt roughly. And that is larger than the than the bandwidth of excitations in the system due to exchange. So you can really focus on the lower doublet. So you take your spin 3/2 Hamiltonian, and as has been done for other materials in this series, you can write down an effective spin 1/2 Hamiltonian by projecting it onto this low energy S plus minus 1 doublet. You then have a pseudo spin 1/2 Hamiltonian, but now you don't have single line anisotropy. Spin 1/2 does not support single line anisotropy, but you have exchange anisotropy. And so this is what this Hamiltonian looks like. So in each chain, you have XY anisotropy, XY exchange, but it's not purely XY exchange. It's the X and Y components are coupled stronger, but the Z component is about 1/4 of the XY. So this is a Heisenberg XY kind of interaction, which is important that the Z components are not totally irrelevant. Then in the next chain, you have the same thing, but of course the anisotropy planes are rotated 90 degrees. And between the chains, the interactions are more easing-like. So the strongest coupling is these components that are parallel to the chain, and the transverse components are coupled with a strength which is 1/2 of this coupling. And this comes just from the projection. So this is, if you just project the spin 3/2 Hamiltonian onto the doublet. And we measured the spin wave spectrum in a quick and dirty triple axis experiment, fit the parameters, and so just to give you an idea, the in-chain coupling is 0.8 millivolt, the zigzag coupling is 0.35 millivolt, but the system has a gap. And if you just had perfect XY anisotropy here, the spectrum would be gapless. To explain the gap, we need to introduce, and this is allowed by crystal symmetry, a tiny in-plane Ising term for the chains. And that is about 10%. But this is mostly an XY system, and you have about 10% of in-plane anisotropy. So you take this crystal, you put it into a good neutron spectrometer, and you see this, and you say, wow, this is really cool. So there are two parts. The high energy part, we understood right away, comes from transitions from the plus minus spin a half to plus minus spin 3/2. So these are outside of the physics that is described by this effective Hamiltonian. I will focus on this low energy part of the spectrum. So this is low temperatures. The material orders magnetically at 1.3 K. We have done a proper neutron diffraction experiment and honestly solved the structure, and it's a very simple collinear structure with spins parallel or anti-parallel to the chains. This is only natural because for the two chains in the triangular plane, this direction is the common direction within the anisotropy plane. Plus, you have this small delta Ising-like anisotropy, which also favors this direction. So this is a very simple commensurate sprite phase that you get below 1.3 Kelvin, and this is low temperature, so this is in the ordered phase. And once you see a spectrum like this, and this is like 12 hours on LET to measure that, you are immediately reminded of what we were shown yesterday, these classic data by Radu on cobalt narbate, which is an Ising chain material, or another Ising chain material. This is an antiferromagnetic chain material, barium cobalt vanadate, studied by Beatrice Grenier and Sylvain Petit and others. And similar material was also studied by Bella Lake and Fabian Essler. So it looks like what we're dealing with is these Zeeman ladders, which is an hierarchy of bound states of domain walls in Ising spin chains. With two caveats. One is that these are not Ising spin chains, and they are predominantly XY spin chains. And number two, they're not isolated spin chains. They are coupled with an interchain coupling, which is, I don't know, 40% of the in-chain one. So, one thing at a time. The almost is XY and not Ising, that's not a big problem, because it turns out that even 10% of in-plane anisotropy already allows you to have a very narrow domain wall. The width of a domain wall in an XY spin chain where Y coupling is 10% stronger than the X coupling is only 2 lattice spacings. So the chains, they do support domain walls. That is no problem. And as for triangular lattice, well, let us look at special wave vectors. Q equals 0.5 along the chains, and Q equals 0 along the chains. And at these special wave vectors, interchain interaction cancels out at the mean field level completely. So in some primitive sense, at these wave vectors, you expect really isolated chains. So I'm going to show you cuts along these lines. Here is how the spectrum depends on momentum perpendicular to the chains at these special wave vectors along the chains. So 0.5 here, 0.5 here, and here versus H, and here versus L. And you see two things. One, you see that each of these bound states, or whatever they are, is completely flat, which tells you that these states are not propagating between chains. They're sitting in one place. They're only propagating parallel to the chains. And the other thing is that there is no substantial intensity modulation in the perpendicular direction. So here I'm plotting intensity of, for example, the first mode versus transverse momentum. And the dependence that you do see is, or here, is entirely explained by the form factor of the cobalt ion and by a polarization factor, which for this case is a transverse polarized excitation. So there is no modulation, means there is no correlations between chains. It means that these are one-dimensional objects. One-dimensional objects that propagate only in one dimension. And if you do the cuts here now here's the same data as a scan, you see this very nice sequence of peaks. You can do it at 0.5, you can do it at an integer value of k. K is the chain axis. And you can do it either with neutrons or with terahertz, so this is a zero-wave vector. And you see essentially the same sequence of lines. So our interpretation, based on what I just said, is that what we're dealing with is bound states of domain walls in a single chain. And because there is perfect frustration between chains, so you can move these guys, these domain walls, as far apart as you want, the interchain interactions within the triangular plane couldn't care less. So if this were the case, then you would just have a continuum of two kink states in your spectrum. However, there is also weak coupling between the layers, between the triangular layers, and that one is not frustrated. So as soon as you get long-range order, you have these spins here that are between the two domain walls that you have created that are unhappy because they're now pointing parallel to the spins that they want to be pointing anti-parallel to. And you immediately can see that there will be an effective linear potential between these domain walls. The further apart you pull them, the higher the energy, which means that the force that is pulling them is independent of distance. This is the typical situation that you also have, of course, in the Ising chains. And then it's a problem of two particles in a linear potential. And in free space, this problem is very elegantly solved. Everybody knows the solution for a quadratic potential. That's your harmonic oscillator. They're equally spaced. But for a linear potential, they're not equally spaced, and they're spaced according to the negative zeros of the Airy function. So there is the energy to create one domain wall two times. So you need two domain walls to create an excitation like this. And then something that scales with this Zi. And the coefficient here, it depends on two things, on the strength of the interaction, the force, and on the kinetic mass of these domain walls. And the kinetic mass we can figure out by fitting this dispersion of the first bound state. And the second derivative of the dispersion here will give you the kinetic mass of a single domain wall. So we know the kinetic mass, and therefore we can extract the force that is pulling them together. Turns out to be the force of gravity between two people at a distance about 4 kilometers. So that's a pretty small force, but enough for our experiment. And then what you do, you plot the energy of these bound states that you have measured versus the value of each of the negative zeros of the Airy function. And what do you know, at least for large indices, for the higher energy bound states, you have a very nice linear dependence. So this is where you get this coefficient from. But for the first three, at least, there seems to be some deviation. You're not surprised. You're not surprised because this is not an Ising chain. And it's a XY chain with only 10% Ising anisotropy. And therefore, the domain wall is not one bond. It looks like this. This is an EL domain wall. And if you do very simple classical simulation, you will find that for 10% in-plane anisotropy, the size of the domain wall is about 2 lattice spacings. So once the first bound states, which are small size bound states, where the size is comparable to the lattice spacing, they will be affected because the domain walls will be overlapping. They will not be separate. There is another subtlety here that is not often discussed, and namely that this problem has two length scales. One length scale is the lattice spacing, but the other length scale is the size of the bound state. The higher energy of the bound state, the bigger it is, but the first bound state has a certain size. And you can use this formula only if you are in the limit of very small lattice spacing. So you have two particles in free space. And if the lattice spacing is bigger than this characteristic size, then it is this naive picture which is more appropriate, where the nth bound state simply corresponds to n flipped spins, and then the distance, the energy is simply proportional to the number of the bound state, rather than scaling as here. And we can estimate from our data that for our material, the size of the first bound state is about 2 lattice spacings. So by the time you get to the 4th or 5th bound state, that bound state is big enough not to be too much affected by the discretization that is provided by the lattice. The other subtlety is the issue of polarization. Because if you look at this cartoon, you will see that the even states, they have an even number of flipped spins and therefore have the same total spin as the ground state. And that means that this is a longitudinal excitation. Whereas the odd ones, they have a different spin, different by 1, so these are transverse excitations. And you would have 2 Zeeman ladders in an antiferromagnet, one with longitudinal, one with transverse excitations. And we see only 1. But there is a good reason for this, and namely that in our case, the potential is very weak. And if you calculate what is the splitting between the 2 Zeeman ladders, that is the difference in energy between this picture and this picture. And this is of the order of lambda b, where lambda is the force. And in our case, lambda b is 0.03 millivolt. And if you look at our spectra with neutrons, you would never be able to resolve 0.03 millivolt. So we have 2 Zeeman ladders that are laid on top of each other, essentially. One for longitudinal, one for transverse polarization. And this is very different in barium cobalt vanadate, where lambda b is 0.3 millivolt and very easily seen with neutron scatter. Good, this is 1D. So, but what now happens away from these magic wave vectors? And here is my picture again. So I'm showing you now a cut here and a cut here. And this is the dependence on momentum transfer in the triangular plane. And you see 2 things. One is that you get a dispersion. It's very weak, admittedly, but they're no longer just flat. And moreover, if you plot intensity versus wave vector, there is absolutely no way, no matter how you combine polarization factors, that you can explain the very rapid fall-off of intensity by polarization factor and magnetic form factor. This means that these excitations, they live in more than one chain, they involve correlations between chains, and that they also move in the triangular plane. And this is something that we only understand at this hand-waving level, and it would be really nice if theorists would help us understand this more quantitatively. Also, if you squint, you will see that there's very interesting crosstalk between different bound states. I start with the first bound state here, I follow it through the brilliant zone, and I come to the second bound state in the next brilliant zone, and vice versa. So somehow, you start with an object that lives in one chain, then as you move in reciprocal space, it becomes an envelope correlated between chains, then comes back into an object with one chain, but a different one that you started with. So it would be really nice to understand this theoretically. I don't have much time, so I will just show you the other interesting aspect of this material, and this is what happens in applied magnetic fields. So here is the phase diagram. Everything I was telling you today happens at 0, that I told you so far is at 0 field. But this is magnetic field in Tesla, sorry, the label is missing. And if you apply the field along the chain axis, you get as many as 5 different phases. And this is C over T plotted here, so you immediately see that the first phase is gapped, and this we already saw with neutrons. The second one is not, the third one is gapped, and these are probably also gapless. And of course, each of these phases has its own excitations, and these are the field-dependent measurements with terahertz absorption, which we have not properly analyzed yet. This part here, is the field dependence of the Zeeman ladder. This is what we heard about yesterday for the cobalt niobate. And then you have all completely different excitations in all the phases. So I'm not going to go into details here because we're just starting to understand what this means. So let me show you what these phases are. Well, first of all, you can measure magnetization. There is a linear term in magnetization that comes from the mixing of the lower doublet and the higher doublet. So it's a Van Vleck-like susceptibility that is always there. But if you subtract that, you measure it above 5 Tesla, you subtract it, you get a very nice one-third plateau here and a very nice zero magnetization plateau. So we have done neutron diffraction experiments in all these phases, and we have solved them. So this one is the stride phase, here and here. This one is really a one-third plateau, so it is an up-up-down state. But what is very interesting is that this guy over here, in between them, it's a spin density wave. It's a longitudinal spin density wave. So let me show you, we don't have good inelastic data there, but we do have nice diffraction data. So this is the triangular plane in reciprocal space. And these are your nuclear Bragg reflections here. And these are your magnetic Bragg reflections. And the hexagon here, this is the Brillouin zone of the triangular lattice. And you see that they're at incommensurate positions, and the incommensurability vector depends on the magnetic field. Not only does it depend on magnetic field, it exactly equals to the magnetization, to the pseudospin magnetization of the system. So here is the measured pseudospin magnetization and measured propagation vector. And you see that, so first you don't have the spin density wave until the first phase transition. Then you have the phase transition, you have a field-dependent propagation vector, and then it locks in onto one-third and goes into the plateau state. So this is a one-dimensional thing. I mean, you understand that in a spin chain, in a magnetic field, you have incommensurate longitudinal correlations that are also critical, just like the commensurate transverse ones. But the transverse ones, and this is something Oleg explained to me many years ago, the transverse ones are frustrated by the triangular coupling and do not order, but the longitudinal ones are not frustrated, or at least not entirely, and they produce this spin density wave phase. So this is one phase that we have identified, and we have also recently identified this phase over here, which happens to be very similar to this one over here. So both of them, we have not solved the magnetic structure, but we have enough data to do it, and we will eventually do that. This is an incommensurate phase, but one for which the incommensurability is field independent. And this reminds you of what you would classically have in a distorted triangular lattice, and namely a Healy magnet or a fan structure for a planar system. And then the propagation vector is simply given not by the external field, but by the ratio of exchange constants. And okay, from this calculation, you get J prime over J roughly 0.2. In our case, it is a lot bigger. But this is just a naive classical way of looking at it. So it is probably something like in each of the easy planes, it is a fan structure. And a fan structure has two branches, has a phase-on mode and a longitudinal mode. And indeed, in the spectrum, we see very nice acoustic and optical magnetic excitations in this phase. And I have no idea how to analyze the spectrum. So we have these beautiful data, so if anyone can jump in and help us do that, would be very helpful. Okay, this is my summary. It is a curious spin model, but the one that was very interesting physics, especially once you start applying a magnetic field. I claim that this is probably one of the first examples of a hierarchy of bound fractional excitations living in and propagating in a two-dimensional model. And it has a really cool phase diagram illustrating many of the phases, at least in spirit, that I showed you on that, from that theoretical paper. And so that would be the end of it. I want to show one more slide as a warning to all the theoreticians. And this is this slide here. What we did, we took a crystal of this material and we glued two electrical contacts on the sample, and we measured the capacitance, and we plotted capacitance versus field and temperature. And you immediately see that the phase diagram that I have shown you measured with calorimetry just jumps back at you. And this means that each of these transitions is associated with very strong lattice effects, so magnetostriction. And not only that, we have measured ultrasound attenuation and ultrasound velocity, and in all the phase transitions that the system goes through in magnetic fields, you see different kinds of anomalies in the speed of sound. And this is what I'm becoming convinced of, that in all the quantum magnets that we happily describe with just spin models, really there is the gorilla that has never noticed, and that's coupling to the lattice and magnetostriction. So with this, I thank you for your attention.
Thank you very much. Sasha?
Does anything happen at the crossings of these bound states?
To the resolution that we have, there is no anti-crossing. That this one and this one, they really cross. And that would mean that they're somehow different in symmetry. Is this your? Maybe we just don't have the resolution to see that, but to the best of my ability, they actually cross.
Thank you.
So kind of a related question. So if I understood right, your picture is as you go from one of these sets of branches to the next Brillouin zone, you cross over from
the first one to the second one, right?
Yeah, from one wave packet.
Yeah.
The wave packet, it goes from one chain to the next.
Yeah.
This sounds like a lot like physics that people talk about, like in terms of Fowler's pump in a churn band or something like that. So is that something like that's going on here? There's
I don't know.
Physics?
I don't know. All the thinking that we did was at the special wave vectors, and here I'm just throwing that at you and hoping for some input.
That's what it seems like, something like this.
Yeah. Thanks a lot for a very good talk. So about your last slide, do you have also temperature dependent on the of sound attenuation?
Yes, we do. We haven't published that.
At given fields, yes.
So there was one problem here, that what you measure, you don't measure sound velocity.
You measure the change.
You need, and not even that, you need to know how the length of the sample changes. So you measure time in the sound velocity experiment, and this time contains change in velocity, but also change in the length of the sample. And to measure the change in the length of the sample, you need a proper dilatometer. Because if you do a measurement like this, when you just glue two contacts to your sample, it is sensitive to change in length, but it is also sensitive to transverse shrinking of the sample, and you cannot separate them. So we're now building a proper dilatometer to sort this out. But yes, temperature dependence we have. We just need to deconvolute this signal into a change in velocity and change in sample size.
So I also comment on this stuff here. So I think the statement in the one-dimensional models is that the divergence at the quantum critical point of composability is so big that there's kind of that you have to take into account the feedback. Honestly, I forgot that maybe you get first order phase transition.
No, this is Larkin-Picken,
yes,
who ages ago said that whenever you have, that in most magnetic phase transitions, you have a coupling to acoustic phonons. And at the end of the day, you never have a continuous phase transition.
Yeah, it depends.
It depends. It depends.
There's two cases: one when the order parameter comes linearly to the lattice, but here you couple only to the mass term. But I think the 1D singularities are so strong that also in this case you get a diverging feedback. But I forgot what the answer is, whether it's now first order or whether it's just a classic.
Some of these are definitely first order. Some of these phase transitions are definitely first order. For example, the transition from the commensurate phase to the spin density wave phase is first order, guaranteed, thermodynamically also. But the locking in of the spin density wave might be second order.
Yeah, very quickly, back to the line of questions about bound states. So you said the first one goes into second one and second one goes into first one in two different Brillouin zones, right?
No, that's what it looks like to me.
Yeah, that's what it looks like.
Yeah.
I have a naive question. What happens with the third one, with the fourth one, if you can say something about this?
If you look at this picture, it seems to me that the third and fourth also exchange places.
So it's exchange of doublets.
Yeah.
Okay.
No, so for theorists, I mean, this resolution can be improved. There are better instruments, and if there is a good motivation for looking at this more carefully, also in the crossing thing, it is possible.
Leon?
Yeah, beautiful talk. I have a question which is maybe not entirely fair because it's a sort of a theoretical question.
Okay.
But when you, so you have a system which is actually XY-like with a small anisotropy, and you drew this kind of classical picture of the domain wall. So for such a system, classically, the spin could rotate in two different senses in the domain wall.
Yeah.
Okay. So is there any remnant of that?
Well, not in the spectroscopic data. Yeah. And so I drew this picture here because this was our first interpretation of why we have deviations here. And actually, only later I realized that probably the main reason for these deviations is the rather large lattice parameter compared to the size of the.
Yeah, well, I'm not really sure if that should survive quantum fluctuations.
Yeah.
Maybe because they're not so small, but one could imagine.
So it's a good question for you. For you
That's
to
why
answer.
I said it wasn't fair, but I'm still asking you. It's what you get for explaining the theory too well.
I'm interested in the spin density wave state that you indicated, and also, so I have two questions about it. One, do you think that at low temperatures this will be squared up so that it's actually some sort of like box-like shape, or do you really think the moment changes in space?
Well, we see only one peak. We do not see any harmonics, and we have looked for them. I mean, not in this scan, but on a proper diffractometer. So it really looks like a very fairly sinusoidal modulation of the longitudinal component. And it's not like we just see a peak. The peaks are strong enough in the spin density wave phase. We were able to measure, I don't know, 4 dozen of them and do the representation group analysis and everything. So this structure is solved, and it is really very similar to a sinusoidal spin density.
And do you think that's related to the spin 1, spin 0 type of the copper?
Because it's, to me, it is related because it scales with magnetic field. I interpret it as a purely one-dimensional effect and the field-depending nesting of the spin on Fermi surface, of the fermionic Fermi surface when you do the Jordan-Wigner mapping.
Okay, then I have just one more small thing. Maybe it's completely incorrect, but I remember Bernhard Keimer's work on the spin piles transition, where you have some kinks and then.
Yes, it's very similar.
So you think that's a similar transition?
It's very similar, and I remember that Genshirani spent an unholy amount of beam time looking for a Zeeman ladder type spectrum in copper germanate.
Yes.
Precisely because he was hoping to see something like that.
I see. So at the low field spectrum, you think it looks kind of what was expected for copper germanium oxide?
I think so, yeah.
Thank you very much for your talk. And my question is related to the last slide about magnetostriction. So could you explain again?
That was just a teaser. That was just a teaser, yes?
Yeah, so what was the measurement technique here?
So you take a sample and you glue, thin plate, and you glue 2 contacts, so big plates, conducting plates onto the 2 sides.
So
and you measure capacitance.
Standard capacitance dialectrometry, okay.
Yeah, and the problem is, the reason this is difficult to interpret, even though it looks so beautiful, is because you have this, but you also have the shrinking of the sample, and the contacts are glued, they will also shrink.
Yeah.
So you cannot separate those.
I will contact you later.
Thank you, Andrey, for a very nice talk. So one question about the breeders. Normally, when the breeder has high enough energy, it can decay into smaller breeders. And
could you repeat this?
When the breeders, have high enough energy, they can decay into smaller breeders. A big breeder can decay into 2 small breeders, and that energy is twice the gap. But you seem to see sharp breeders even above twice the gap.
So you're talking about this, right?
Yeah. So
well, this gap is pretty big.
It's 0.4, right? Twice is 0.8. And
this is 0.4. Yeah, you're right.
But you still see sharp breeders above 0.8, right?
So we do not see anything that looks. So if there is continuum here due to decaying or broadening, we do not see that. It looks to within our resolution, we really have single modes.
Even about 0.8, you mean twice the gap?
Yes, yes. Because you see, when you go higher, you of course lose intensity. But what we can see.
But do you understand why there is no decay? I mean, so why?
I think there is. I think that we just don't have enough resolution intensity to see this properly.
I see. Okay.
That is my guess.
Thank you.
So beautiful talk. These bound states and the fact that they are confined to chains for some particular momenta, do you think there is a way to see any remnants of that in thermodynamics, like specifically? So these are kind of slow excitations, maybe high density of states. As we go down in temperature.
Well, you should be able to model your specific heat with a purely one-dimensional dispersion. Which is that's what I'm saying, that the first excitation after the gap is purely one-dimensional. And you know the curvature of the parabola, and you know that there is no dispersion in the perpendicular direction, and you can figure out what the specific heat will be like.
Any hints of that?
We haven't tried that yet. But not entirely true. If you just analyze the specific heat, and you just fit it to an exponential, you get more or less the right gap energy. But whether it's the dispersion on top of this is 2 or 3 dimensional, that becomes very difficult to tell apart.
I'm just coming back to the first points of the crossing 1 and 2. You mentioned that longitudinal and transverse are nearly degenerate in your case.
Okay, so
are they crossing together?
So
is there obvious
we were able to do to some extent this poor man's polarization analysis, and I can say that the first mode is transverse polarized, and the second one, and you can see this probably here. Yes, that's the first mode. The second mode probably has some component from the longitudinal part. The second one is definitely mixed. But we have a proposal in for a polarized neutron experiment to sort this out because the crystals are big enough for polarized neutrons.
Are there any further questions? If not, well, let's thank Andrey again for a beautiful talk.